Hey guys, so today I'm gonna be solving this problem that Akil gave me step by step. So let's read it off. Which of the following provides the most rigorous mathematical justification for the existence of the zero-point energy? Option A, the Heisenberg uncertainty principle qualitatively qualitatively suggests a minimum energy, but it is the application of the boundary conditions to the Schrödinger equation that quantitatively yields the exact value E sub 1 is equal to h squared divided by 8 ml squared. B, the 0-point energy arises because the potential energy V of x is 0 inside the wall. According to the classical equipartition theorem, the average kinetic energy must be 1/2 k sub b times t, which is positive for any t which is greater than 0. C, the wave function must be normalized to 1, so i.e. the integral from 0 to L of the absolute value of psi of x squared dx is equal to 1. This requirement forces the energy to be a positive value, as a zero energy wave function could not satisfy this condition. And D, the existence of 0-point energy is a direct consequence of the wave-particle duality of the matter. The de Broglie wavelength of the particle must perfectly fit within the box, and the smallest possible wavelength is 2L, which corresponds to a positive momentum and thus positive kinetic energy. So let's go ahead and get this started. So our potential is, let's see if it wants to work with me, V of x is equal to 0, which is greater than x, greater than L, and V is infinite outside. And the time-independent Schrödinger equation inside the wall, which is negative negative h squared over 2m times d squared psi over dx squared, which is equal to e of psi. So first what we got to do is we got to solve the differential equation. So we're going to let k be equal to root 2me divided by h. And the general solution that we can get from this is psi of x is equal to a times sine kx plus b cosine kx. So what we have to do is we have to apply boundary conditions. So for infinite wall forces, which is psi 0, which is equal to psi of L is equal to 0, we figure out that psi of x is equal to a sine of kx, because psi of 0 is equal to 0, and b cosine of 0 is equal to b, which is just equal to 0. So what we're going to do is we're going to let psi of L be equal to 0, which is equal to sine of KL, which is equal to n times pi, where n can just be 1, 2, 3, and so on and so forth. So what we want to do next is, I've actually ran out of room, so I'm going to start another one. We want to know that the quantized k in energy, so k sub n is equal to n times pi divided by L, which then turns into E sub n is equal to h squared k sub n squared all over 2m, which is equal to h squared, it's a horrible squared, all over 2m times n times pi all over L squared, which really it just becomes n squared h squared divided by 8ml squared. So the 0-point energy appears automatically, and the ground state is n is equal to 1. So what we're going to say is E sub 1 is equal to h squared over 8ml squared, which is greater than 0. And a true zero energy, which would be just E is equal to 0, would imply that K is equal to 0, which would again imply that psi is equal to 0 and psi is equal to AX plus B. And so psi of 0 is equal to psi of L. And we get that A is equal to B equal to 0 because it's the trivial non-physical wave function. So E is equal to 0 is impossible. The lowest allowed energy can only be strictly positive because that's the 0 point energy. The entire result, including the exact formula, comes rigorously from usually like solving Schrodinger's equation and enforcing boundary conditions, which makes the answer be number A. Some further evidence I'd like to present is that B uses the classical equal partition theorem that breaks down in quantum systems at low T and can't derive the exact ground state energy, so it's not rigorous here. For C, the normalization of the integral from 0 to L absolute value of psi squared dx is equal to 1. It doesn't force that E is greater than 0 because normalization fixes the overall scale of psi and not the allowed energy. So the exclusion of E equals 0 comes from the differential equation plus boundary conditions, not from normalization. And for D, de Broglie's wave in a box intuition, lambda, which is this symbol right here, looks funny. It has to fit in a box, and the smallest lambda is equal to 2L. And it's a useful physical picture, but it's semi-classical, so it doesn't by itself constitute a full mathematical derivation from Schrodinger's equation, and it won't quite deliver the framework, so it's not the most rigorous. And overall, inside the, I'm gonna make a little conclusion here. Inside the infinite well, 0 less than x less than L, v equal to 0. So the time independent Schrodinger equation is negative h squared divided by 2m psi equal to E times psi. It's a horrible E. And infinite walls means psi of 0 is equal to psi of L, which is equal to 0, 2. So from psi to 0 equals 0, we get B is equal to 0. So psi of L equal to 0. So we get sine of KL is equal to 0, which then turns into KL, which evolves into n times pi. Thus, K sub n is equal to n times pi divided by L, with E sub n is equal to h squared times k squared n all over 2m, which later evolves into n squared h squared all over 8m. That's a horrible 8. L squared. And the lowest energy is n is equal to 1, and E sub 1 is equal to h squared divided by 8ml squared, which is greater than 0, which was the 0 point energy. And let me start another one again real quick. If we try that E is equal to 0, the only solution obeying the boundaries is psi is equal to 0, which is unphysical. So E of 0 is basically forbidden, and therefore the most rigorous justification is solving this Schrodinger equation with boundary conditions, which is option A. B is classical and fails here. C misuses normalization. And D is a picture, not a derivation. Thank you guys for watching. Comment, like, and subscribe, and I'll see y'all next time. Goodbye.